So in today's session, we'll be discussing about short circuit calculation. Okay. So first of all, what do you mean by short circuit? Okay. So short circuit basically, when two phases come in contact or any two current carry conductors come in contact, there will be a short circuit. That means the current which is supposed to flow through two different cables are coming in contact and it is flowing through one. So there will be a oversurge of power will be there in that case. So if a small equipment means it will be damaged, so that we have to protect our system from the short circuit. For that, we will be usually providing earthing. So short circuit we cannot avoid every time. It's an accident, it may occur. So if that occurs means we have to protect our systems from the overcurrent. Okay, so that means we will be providing earthing for that system. Okay, so earthing means whenever a short circuit occurs, the extra current will be taken out or it will be earthed through the earthing cable. So that's the purpose. Okay. So in order to provide earthing, we have to find out how much will be the short circuit current. Okay. So in this calculation, we'll be doing an assumption that what if a short circuit occurs, how much short circuit current will come into a system. Based on that, we have to provide or we have to choose a appropriate earthing or the size of the earthing rod, pipe, whatever earthing you are following. So we have to calculate that. So in today's session, we'll see how to do the short circuit calculation. Okay. And one more thing, as I mentioned before, all these things will be taken based on assumption. What if a short circuit occurs? Okay. So this is the a basic about the short circuit. Okay. So in order to find out short circuit current, we are using a method that's called impedance method. Okay. So impedance means it's the sum of the opposition or the resistance in a system. So resistance means the opposing factor. Okay, so whenever current is flowing through a conductor, there will be some opposing factors will be there. So that sum of the resistance or the opposition current or which is present in the circuit is called what? Impedance. And the equation for impedance will be denoted as Z. So Z is equal to root of R square plus X square. Okay. And the R is resistance and the X is reactance. So resistance and the reactance are the what factors which I mentioned before. Factors which will be opposing the flow of current. So the sum of these is called the impedance. Okay. So this is the method we are following. Usually we'll be following to find out the short circuit calculation. Okay. And once we got the equation for impedance, okay, so an important one, impedance method. So once we got this value, we have to find out. So if you consider a circuit or a system means we'll be having cables will be there. Then we'll be having equipments will be there. Suppose if we consider our a transmission system, in that case, the cables are what having a certain impedance will be there, and also the equipment in that case it will be transformers also have certain impedance or the resistance value will be there. So we have to find out what are the impedance of cable and how much will be the impedance of the equipments here. For that, we have an equation that's the impedance of cable is equal to root of R square plus X square divided by number of cables into cable length. So this is the equation to find out the resistance and the reactance value of the cable. Okay, so why this is important means through the cables, the current is actually flowing through the cables. So we have to find out how much resistance these cables or these equipments are offering. So for that, we are using this equation. Okay. Then next is per unit impedance. So per unit impedance actually is a unit value. It will be always less than 1. Okay, so if we got a value more than 1 means it is actually wrong. So it will be always less than 1. And per unit impedance of cable is equal to ZC. ZC means the impedance of the cable into base MVA divided by base kV square. So here ZC as explained, this is the impedance of the cable and base MVA. So base MVA will be considering as a common multiple. So most commonly we'll be taking 10 as the base MVA. As you can take 10, 20, you can take that. But as per standards, we'll be considering as a minimum of 10 MVA. I'll explain why. And divided by base kV square. So base kV square means the supply voltage through that line. So whatever is supply voltage, suppose if it's 11 kV means 11 kV square. If it's 33 kV means it will be 33 kV square. So that is the base kV, the supply voltage through that line. That's it. Okay. And why base MVA we are considering 10 means if you consider the so a small circuit or the system is shown here. So we have to find out the short circuit current for this particular system. So here you can see that we are having a power station. That capacity is 100 MVA and the supply voltage is 33 kV. From there, we are distributing it to three transformers, transformer 1, transformer 2, and transformer 3. So this is the primary distribution side. Here, you can see that this is the transformer 1, 2, and 3. Then transformer 4 is actually the secondary distribution, that is the step distribution transfer shown here. Okay. So in this case, 100 MVA is given. 100 MVA is the, so that 10 is actually common in what? 100, right? And if you have 200 MVA, 300 MVA, 400 MVA, whatever is your power generation, megavolt ampere, 10 is actually common for all the system. So that's why as a common multiple, okay, so for a common multiple, we are considering 10 as a minimum. Okay, so that's it. So here we have power station, then we have four transformers, and we have what? Cables connecting each transformer. So we have T1 C1, T2 C2, T2 C1, and T2 C2 means transformer 1, cable 1. So this is the primary side of the transformer, and this one will be the secondary side of the transformer. So on the primary side, the voltage will be 33 kV. So you can see that it's from the power station, it is supplying 33 kV voltage, right? So that the primary side of this transformer will be 33 kV, and the purpose of the transformer is to what? Step down the voltage, right? So that in the secondary side, it will be 11 kV. Okay. Then next we have transformer 2, same way. Primary side will be 33, secondary will be 11 kV, and here also you can say it's 33 primary and 11 kV secondary. And the primary side and secondary side we have cables, and for that cables, the cable size is mentioned here. 2 runs, 3 core, 150 mm square, and the length of the cable is 25 meter. Same way for T2 also, sorry, T1 C2, 36 meter, 3 runs, 3 core, 300 mm square. So like that, for each cables, the corresponding size is given. And for the transformers, for each transformers, its capacity is given here. That's 7.5 MVA, 1 MVA, 750 kVA, then 500 kVA. Also, the impedance is also given. Percentage is that means the impedance of this transformer 1, 2, and 3. Impedance means resistance. The resistance offered by that equipment. So here it is what? 8%. That's it. Okay. And when it comes to this side, T4C1 or the transformer 4, here you can see that the primary side will be 11 kV. Secondary will be 440 volt. Okay. And for that, for each cables, its R value and X values are given here because the resistance value will change based on the cross-section area. So whenever the cross-section area changes, its R value and X value will change. And again, these are not standards. It will change based depending upon the manufacturer. Okay, so you can get these values from the manufacturer or from any other source. You can what? Get the resistance and the reactance value of that selected cable. And the resistance is given in ohm per kilometer. Okay, so for example, if you take a 150 mm square cable, for 150 mm square cable, the resistance value is 1.157 ohm per kilometer, and the reactance value is 0.0745 ohm per kilometer. Similarly, for each cables, for this one, for this calculation, I have only taken for these three cables because these are the only cables which I'm using in this case. So I have only given for this one. I'll share the table. If it's available, I'll share that. That's the resistance value and reactance value for each cable is given. So based on our equation, we can what? you can easily find out the short circuit current. First of all, we have to find out the impedance of the cable for T1 C1, T2 C1. For individually, we have to find out. Then for the equipment's transformer, for transformers, we have to find out. Then the fault is here. You can see that fault 1, fault 2, and fault 3. So here we are going to assume that if a short circuit occurs over this side, how much will be the short circuit current which will become to this side? And if a short circuit occurs at fault 2, how much will be the short circuit current and the power? Then fault 3. So for each side, we had to find out the short circuit current. Okay. So this is the question. So we can start with that. So any doubt in this one?
No, sir.
So now let's start with that. So first thing, we have to find out the impedance for the cables. So here we have one T1 C1, T1 C2, T2 C1, T2 C2 like that. 1, 2, 3, 4, 5, 6, 7, 8. So we have total 8 cables. So we have to find out the per unit, not per unit, the impedance of the cable. After that, we can go to the impedance of the cable. So equation is root of r square plus x square divided by number of cables into cable length. And number of cables means the runs of the cable. So here you can see that 2R. Means 2 runs means 2 number of cables. 1R means 1 number of cable. Okay. Also, it's cable length. It's also mentioned here. It's 25 meter, 36 meter, 32 meter. So it's already given here. Just to what? Substitute the values. And in our equation, the R value and X value, resistance value, reactance value, for we have to get for 150 mm square cable. And for 150 mm square cable, it's actually given here the R value and X value. So just what? Substitute the values depending upon the cable size. Okay, so you can start with that. First one, impedance of the cable T1 C1, and the R value is 0.157 whole square plus X value is 0.0745 whole square divided by, next is number of cables, right? So the cable size is 2R. That means, yes, 2 number of cables. So divided by 2 into cable length. Cable length is given in meter, 25 meter. And our resistance value is given in per kilometer. So we have to convert the meter to kilometer. So that will be easy. So that means 25 into 10 raised to minus 3. You will substitute so that you will get 0.002174. That's a resistance, or that's a impedance of the cable. And one more thing, when you complete the equation, you will be getting a smaller value. So at least take a 4 value after the decimal point. Okay. If you take 2 or 3 value, the value will be very small. So just consider at least a 4 values after the decimal. Next, T1 C2, transformer 1, cable 2. Okay. Same way here itself. Its size is 3 runs and 300 mm square. So 3 runs mean 3 number of cables, and 300 mm square. This is the R value and X value for 300 mm square. So 0.078 and 0.075 ohm per kilometer. Similarly, substitute the values so that we'll get, and the cable length is 36 meter. Okay, so 36 into 10 minus 2 minus 3, you will get 36 into 10 minus 3, you will get 0.00129 ohm. Got it? So similarly, find out the impedance of the cable for all the cables up to T4C2. Up to here, T4C2, you have to find out the impedance of the cable. Okay. Now, once you got these values, you can easily find out the per unit impedance. Per unit impedance means impedance of the cable into base MVA divided by base kV square. Okay. So as I explained, this will be the value which we got here. And base MVA, we are considering 10 as the minimum base MVA. And base kV square means the supply voltage through that cable. Okay. So we can start with that per unit impedance of the cable. So let's see. So we have first, you can start with the T1 C1 again. So per unit impedance of T1 C1. That is transformer 1, cable 1. Set C, you can get from here. That is 0.002171. Okay, so you substitute that value. Base MVA, we are considering 10 as minimum. Then base kV square. So base kV square means this is the T1 C1, right? So supply voltage through this line is 33 kV. Okay, so in divided by base kV square means 33 square. Again, you will get the value here. Now, per unit impedance of T1 C2, that is transformer 1, cable 2. Okay, so we already have the value 0.00129 into base MVA 10 and base kV square. This is the cable, right? So this is the cable, and here the supply voltage is 11 kV. So 11 square. So once you have done that, you will get 0.000106661. Similarly, you can find for all the cables. Okay, T2C1, T2C2, T3C1, T3C2, T4C1 and T4C2. So when it comes to T4C2, transformer for cable 2, our equation is impedance of the cable into base MVA divided by base kV square. But when it comes to the T4C2, here it is 11 kV. Okay, so it's given in kV square. So again, directly take in kV square itself. And here it is 440 volt. Okay, so the volt you should convert to kV. So that's why here conversion is given here. 440 into 10 minus 3 whole square. That's it. Okay. So that you will get the per unit impedance of the cables. Okay. Got it? Afterwards, the next we can find out the impedance of equipments. Equipment means our transformers. Transformers are the equipments here. Okay. So here again same equation itself. In this case, it will be impedance of equipment into base MVA divided by MVA rating of the equipment. Okay. So the first equipment is our transformer 1. Transformer 1 is this one, T1. And the impedance is 8%. So 8% will be the resistance. So when it comes to calculation, 8% will be 0.08, right? So that 0.08 base MVA. Again, one more thing. If you are considering 10 as the base MVA for this one calculation, throughout the calculation, you have to follow 10. In between, you cannot change. If you are changing means you have to change, start with 20 itself. Okay. And do 10. And MVA rating of equipment means the capacity of the transformer. So the capacity of the transformer is 7.5 MVA. So that substitute that value 7.5. So that 0.1066. Then transformer 2, 0.5% is the impedance. So 0.05 into 10 divided by, it's 1 MVA. So divided by 1.5. Similarly, transformer 4 and transformer 3 and transformer 4. And when it comes to per unit impedance of source is our power generating station. This one. So its capacity is 100 MVA. Okay. And the per unit impedance, again, it's not given here, or the impedance value is not given here. And here I'm assuming a 100% impedance. Okay. So that I will consider 1 into 10 divided by 100. So why 100% means, again, as I mentioned before, this all calculation based on an assumption. What if a short circuit happen here? So we're assuming that here we have a 100% resistance. Okay, so how much will be the short circuit current coming into our system? So 1 into 10 divided by 100, you will get what? 0.1. These are the impedance value of the equipments: 0.1, 0.8, 0.66, 0.5 and 0.106. Okay. So now we have got all the values we require. We have the impedance value of cable, per unit impedance of cable, and per unit impedance of the equipment as well. So once we have got this one, we can just simplify our diagram. Okay, so we can find out what is the per unit impedance of each cable and our each equipments. Okay, so just simplify that by just drawing a impedance diagram. So in this impedance diagram, first impedance is for the source, that is 0.1. We got 0.1. Then per unit impedance of transformer 1, cable 1. So we already got a corresponding value of cable 1, cable 2, cable 3. So all the values we have. So just want to substitute all the values over here. Then transformer 1 impedance is 1.066. So just substitute the value. Transformer 2, transformer 3, transformer 4, and the respected cables. Just substitute all the per unit impedance value. Okay. So once we have added that, just what? Simply sum all of these. Again, we have to sum it in series ways and parallel ways. So you can add these three: C1, transformer 1, cable 1, transformer 1, and transformer cable 2. So these are in series connection. So you can add that directly. Okay. So once you have add that, again we can simplify the impedance diagram into this one. Okay, so 0.1. Then by adding these three, you will get 0.106. And by adding the transformer 2 side, you will get 0.5, then 0.66, then finally 0.968. Okay, so series ways we have added first. Now we had to add in parallel. So these are the parallel function. So we know how to add in parallelly. So 1 by R is equal to, that is 1 by R1 plus 1 by R2 plus 1 by R3. So you can add in parallel as well. So once you add this parallelly, you will get 0.0774. So 0.1 is the impedance of the source side, 0.968 is the impedance of transformer side, transformer 4 side, and the middle part, the primary distribution side, it will be 0.0774. So we got all the impedance per unit impedance of equipment and cables as total. Now we have to find out what will be the short circuit at fault 1, fault 2, and fault 3. The other three things we have to find out. Okay, so clear till here. Any doubts? So this is the first step we have to do after we got the per unit impedance values. Okay. Now we can start with the short circuit power. So first thing we had to find out the short circuit power at fault 1. Then short circuit current at again fault 1. Okay. So here is the fault 1. Okay. And the equation is short circuit power is equal to base MVA divided by impedance. Okay. So base MVA we already had 10, and impedance means this is the impedance 0.1. Okay. So 10 divided by 0.1 you will get what? 100 MVA. So 100 MVA is the short circuit power at fault 1. Okay. Now we have to find out how much will be short circuit current. So current equation is what? I is equal to P by root 3V. We already have the equation. So in this case, it will be short circuit power divided by root 3V. That's it. That's the only change. Okay, instead of a power, we will consider short circuit power. The power we will be getting in the last term. So the short circuit power is 100 divided by root 3 into voltage. So fault 1. So fault 1, right? So fault 1 means here the supply voltage is 33 kV, right? So it will be into 33. That means it is 1.75 kiloampere. Okay, so that's how you get short circuit current. So 1.75. So based on 1.75 K, we'll provide the earthing at fault to 1. Okay. Now fault 2. Short circuit power at fault 2. That is equal to 10 divided. So base MVA is 10. Then impedance. So impedance at point 2 is, or fault 2 is what? 0.0774. Okay, so usually we'll add what? You will, in place of impedance, you'll add this value. But here in short circuit calculation, the thing is again coming to the same term. I'm assuming that first we have 1.75 kiloampere here. Okay, so I'm just assuming, what if the earthing fails here? So if a short circuit occur over this here means at fault 1 means 1.75 kiloampere will come at fault 1. But I'm assuming that if the earthing fails at fault 1, the short circuit current will come to here also at fault 2. The same short circuit current will come to what? Our fault 2 side also. So that the earthing at fault 2 should have the capacity to earth the fault 1 plus fault 2. Combinedly, we have to consider. So that the impedance will be the short circuit power at fault 2 is equal to 10 divided by 0.1. 0.1 is impedance of fault 1 plus 0.2 impedance is 0.0774. We'll add that. Then we'll get 52.26 MVA. Okay. So that the fault 2 should have the capacity to earth the short circuit current at fault 1 and fault 2. That's it. So 52.26 MVA divided by root 3 into 11 will get what? 0.274 K. Okay. So at fault 2, the short circuit will be 2.74. 74 K kiloampere. Okay. Now coming to the fault 3. Okay, so same condition applies here. So when it comes to fault 3, the base MVA is 10 and the impedance will be the sum of fault 1 plus fault 2 and fault 3. Same condition. What if the fault 2 earthing fails? The short circuit current will come to the distribution side. So the earthing over the distribution side should have the capacity to earth the fault at 1 and 2 plus 3. That's it. Okay. So that we'll add these three, then you'll get 8.73 MVA. So that 8.73 divided by root 3 into 4. Here the volt, okay, small mistake is there. Here this is in, here has substituted in kV. But 440 is actually volt, so that it will be 10 minus 2 minus 3 you have to add. Okay. 10 minus 2 minus 3. So that you'll get what? Okay, only this one is a mistake, answer is correct. 11.45 kiloampere. So we'll provide earthing here based on 11.45 kiloampere. Okay, so that's our short circuit calculation. So fault 1, fault 3, and fault 1. So based on these three values, we'll provide earthing here. Clear? Any doubts? Again, actually, the equation is actually a bit lengthy, but the concept is very simple. It's actually many more repetitions coming here because we have 8 cables and 4 circuits here. That's why we are repeatedly doing the three. So I hope the idea is clear. Any doubt in this one?
No doubt, sir.
Okay. Okay, so I'll do one thing. I'll just wind up the session for today. Just practice this one. Tomorrow we can go for the earthing. Okay, so I think we can go for type of earth and the calculation. So based on the kiloampere, how to select the earthing road pipe. So that one we can discuss in the session. Okay.
Okay, sir.